The Mathematics of Epidemics Using Derivatives by Vodcast Group 19. A derivative can be defined as an expression representing the rate of change of a function with respect to an independent variable. Derivatives are usually notated as prime, or the symbol f prime x for a function f of x. The process of finding a derived function symbolically is known as differentiation, and 6 rules apply when differentiating. Rule 1, the constant rule. This rule tells us how to find the derivative of a constant multiple of a function. It can also show that constants differentiate to 0. Rule 2, the sum rule. If h of x equals f of x plus g of x, then h dash x equals f dash x plus g dash x. This rule tells you how to find the derivative of the sum of two functions, and you can use this rule by differentiating each function separately and then adding. Rule 3, the difference rule. If h of x equals f of x minus g of x, then h dash x equals f dash x minus g dash x. This rule tells you how to find the derivative of a difference of two functions, and you can use this rule by differentiating each function separately and then subtracting. Rule 4, the chain rule. If y is a function of u, which itself is a function of x, then the change in y over the change in x equals the product of dy over du and du over dx. You can use this rule by differentiating the outer function and multiplying by the derivative of the inner function. Rule 5, the product rule. If y equals uv, then dy over dx equals u times the derivative of v plus v times the derivative of u. This rule tells us how to differentiate the product of two functions, and you can use this rule by multiplying each function by the derivative of the other and then adding. Rule 6, the quotient rule. If y equals u divided by v, then dy over dx equals v times the derivative of u minus u times the derivative of v, all divided by v squared. This rule tells us how to differentiate the quotient of two functions, and we can use this rule by multiplying the denominator by the derivative of the numerator.
Now I will explain to you the SRI model in terms of a disease. S refers to the number of susceptible individuals healthy and have never had a disease before, but not immune. I refers to the number of infected individuals, and R refers to the number of recovered individuals immune and will not get sick anymore or infect anyone. As discussed earlier, S dash, I dash, and R dash each refer to the derivative of S, I, and R, or in this case the rate at which they would change. So S dash, I dash, and R dash is a frequency such as per week or per day. In the model, susceptible individuals sometimes get sick or infected. Similarly, infected individuals will recover. This is why the rate is important. We want to measure the rate at which susceptible individuals get infected and the rate at which infected individuals get better. Then the rate at which individuals get sick is equal to S dash. This is proportionate to individuals who are susceptible, S, and who are already infected, I. This is because there's a chance that the infected person infects a susceptible person. There is also a constant in front because the amount of times I and S make contact is proportional. R dash is equal to B times I. Every day, a fraction of B of the infected or I individuals will recover. The disease runs for approximately 2 weeks, so we can say every day 1/14 of all individuals will recover. As discussed earlier, S dash, I dash, and R dash each refer to the derivative of S, I, and R, or in this case the rate at which they will change. So the rate at which we go from S to I is A times S times I. The rate at which we go from I to R is B times I, where B and A are constants. Now this means the rate at which people are getting sick or S is changing is negative because people stop being susceptible. The rate at which people are getting sick, or the rate at which I is changing, is the rate at which individuals are getting sick minus the rate at which they are recovering. And the rate at which R is increasing is the rate at which individuals are recovering. In addition, there will be different values of A and B depending on the conditions of the individual is in, such as their diets, living conditions, etc. So A is a transmission coefficient, how easy the disease is spread, and B is the recovery coefficient.
I will quickly discuss a further simple epidemic model. The model will measure the spread of something, such as the spread of cancer in an organ, or the spread of information on an internet-based social networking site. For the sake of explaining this model, the example I have chosen is to utilize the spread of a flu virus in Macquarie University. There are some assumptions of the model, including the students will meet each other randomly and the disease is infectious. We are going to let P be the probability of the person having the flu, and 1 take away the probability be the probability that they do not have the flu. Simply, if one person meets another with the flu, the disease would spread and should spread at a rate of the product P times 1 take away P. The epidemic model is therefore presented to you on the screen. R is the constant determined by how often the students meet and spread the disease. And to sum up, we have a graph to display the spread of a typical epidemic. Initially, it's slow at the start, faster rate in the middle, and then slow at the end. This is known as our logistics curve.
I'll be explaining how we come about the conclusions of this model. Analysis without numerical values. Let's look back at the equation for I dash. I dash is equal to ASI minus BI. We can factor out the I and get AS minus B and the whole thing multiplied by I. So according to this, if S is greater than B over A, I dash will be positive, which means that the epidemic is growing and each day there will be more sick people than before. If S is less than B over A, I dash will be negative, which means that the epidemic is shrinking and people are getting better every day. So we can describe B over A as a threshold, and whenever S is less than the threshold, the epidemic will die off, and whenever S is greater than the threshold, the epidemic will get worse. Next we will talk about what we can do to inhibit the spread of the disease. Our objective is to try and get the value of S to be less than the value of B over A. There are 3 ways of doing this. Firstly, we can decrease A. As stated earlier, A is the transmission coefficient, which describes how easily the disease is spread. For example, this can be done by various methods, from washing your hands to making sure the sick individual stays away from public areas. Secondly, we can decrease the number of susceptibles. This can be done by using vaccines. However, the only limitation with this method is that it must be carried out before the epidemic starts. The third method would be to decrease B. This can be done by using antibiotics, but this is rarely effective. If none of these methods work, however, then the only option is to wait, because sooner or later the epidemics run out of susceptibles, and eventually the number of susceptibles will be less than B over A, and at this point the infection will start to die off.
There are several implications of the conclusions we draw from our SIR model. Each fall into one of 3 categories: social implications, ethical implications, and economic implications. Social implications. As mentioned in our conclusions, one of the ways we can decrease susceptibility is through preventative vaccinations, perhaps even mandatory. Mandatory vaccinations can be paradoxical, in the sense that what may be seen as a practice that is done in the interest of public health may also be seen as a breach of individual rights, namely the right to refuse being vaccinated. John Kamwiri highlights this, pointing out that such common traits of an SIR model in practice, such as isolation, civil confinement, and prioritization, are all invasive practices on libertarian ideals. Ethical implications. In some SIR models, the R does not simply denote recovery, but instead removal. Removal refers to any way an individual is removed from the susceptible and the infectious category. In our conclusions, we stated that a way for individuals to move into this category was through use of antibiotics. However, another way they can move into this is simply through death. This is an obvious occasion where mathematical model comes up ethically short, as it dictates that individuals must move into the R category in order to beat the disease. Economic implications. Epidemics lead to short-term economic consequences in wide areas due to the fact that, by definition, epidemics are widespread. However, generally they do not last for a sustained period. Endemics lead to long-term economic consequences in controlled areas as, by definition, they affect only a small population or area. As disease spreads, a society's economic health deteriorates, which further exacerbates the disease epidemic. It can be seen as a spiral sort of flow mechanism.